In this video, we are going to go over section 7.7, double integrals over more general region. In last section, in 7.6, we went over double integral over a rectangular region. Now, what we are going to do is we are going to extend the idea and then do a double integral. In other words, find the area over non-rectangular region. So take a look at the definition. So instead of x and y just being numbers, last section, you can see that both x and y had numbers involved, -4 to 0, 0 to 5, 0 to 4, -3 to y, -2 to 2, -3 to 4. So you have these 4 points. So it creates a rectangle. However, in 7.7, we are going to have some parts, like for example, one variable, like this x, has a numbers, and the y value a function. So you're going to be having a region bounded by certain points and a curve. So the whole plane that we are looking at is not a nice rectangle, but it's covered by some funky curve. Same thing. I could have y value as a number and then x as a function value. So last time, the order did not matter. In fact, we used the example 2 to confirm that we got the same answer. So dy dx versus dx dy, we got the same. In here, it does matter because we are not just having a number, we are having the whole function. So if we are taking a regular x region, in other words, dx at the end, so we integrate with the y term first and then x. Versus regular y region will be we integrated with the dx term first and then dy. So here I will be using a highlighter again. So let's say the y term, we have function, and then we have y term here, and then x term. And then let's highlight this, y. So if you integrate y, look at you're evaluating the function. Okay, and then in this case, value. And then we are going to have the x as a number. In here, x will be the function. Okay, so same idea. Instead of numbers, you input the function value and we integrate it twice. dx, the regular x region, regular y region, we do have a different answer, so order matters this time. Okay, so let's start with kind of like a warm-up problem just to fill the notation and then how to take the integral over more general regions. So I have first example, evaluate the following integral. We have 0 to 8, and then second integral from 0 to x, dy dx. So these two, the y part was yellow, so this is associated with the y variable. 0 to 8 is your x value. So just like we did in earlier section, we are going to start with the inside and then approach outside. So we integrate y term first and then x. So let's do this one. So we have integral from 0 to 8. Now, respect to y means variable x is a constant. So this is a constant, so you gain a variable. So it will be 3xy plus, the second one will be raised power divided by new power. So you have y cubed over 3. And then going from y equals 0, y equals x. Notice that it's a function, not a number. dx. Okay, now let's do the same thing. Treat it like a regular thing. So we have a 0 to 8. Now the first one, you're going to input the x where you see the y. So you have 3xx plus x cubed over 3. subtract 3x times 0 plus 0 cubed over 3 dx. Let's simplify. So we have 0 to 8. Here I'm going to have 3x squared plus x cubed over 3. And this one, you see that it's 0 dx. Okay, that's good. All these variables end up being kind of like reduced down to 1. So now you have a nice function with just dx. Same thing, I'm going to evaluate. I'm going to integrate it for the second time respect to x this time. So we have term by term, so 3x cubed over 3 plus x to the 4th over 12 from 0 to 8. In other words, we have x cubed plus x to the 4th over 12 from 0 to 8. So we have, let's see, 8 cubed plus 8 to the 4th power over 12 minus 0 cubed plus 0 to the 4th power over 12. So the first parentheses, I have, let me pull out the calculator. So I have 8 cubed, which is 512, plus 8 to the 4th power, which is 4096 over 12. And then this last one is just a 0. So I'm getting a decimal number. So 512 plus 4096 divided by 12, I'm getting the final answer as 853.3 repeated. Okay? So not so much different in a sense, but we are evaluating a whole function instead of number. Okay? So let's try a couple more examples together. Number 2, use the description of the region R to evaluate the integral. So we have the integral, and then we have a function. So the x value here, and then the y value. Notice it is easier in y because you have a number. X is a function 0 to y. So I'm going to set it up. You have two options. You can set it this way. Here's the first way. Here's the second way. Now look at this one. Here you have this. This is how I decide which to integrate it. I have y whole thing as a number, not a function. So I'm going to choose this one over here. Look at this one. You see that? Y is C to D. This number 2 is the exact same format as case 2. You have a x1, 0 to some function. So here is the function part. And then here's the y with the number. So so you can see that the description, just this one, will show, this one tells you that we want to have a regular y region. So this description already tells you that you want to integrate at the x dy. Right over here. dx first and then dy. So let's do that here. So the x dy, so I'm going to put the y part here. And then the x 0 to y. The whole function is 2x plus y minus 3 dx dy. Let's just double check. X term 0 to y, so the first one matches up. 0 to 6 dy. Very good. Okay, now the rest of them, we did it so many times, so it's just integrating twice. Let's start with respect to x first, dx. So it's from 0 to 6. Right over here, we have now we are taking the antiderivative respect to x, so y variable is constant. So this one, I gain a power divided by new power. So I'm going to have 2 x squared divided by 2. So I have x squared term for the first one. And then second one, y is a constant, so we gain a power xy minus 3x. Integrating from x equals 0, x equal y, dy. Okay, let's evaluate. So 0 to 6. So I have y squared plus y squared again, right? Y times y minus 3y. Second one is a 0 squared plus 0 times y minus 3 times 0. In other words, it's just 0 dy. So we have 0 to 6. I have, it looks like 2y squared minus 3y dy at the end, right? This one is a 0. I have 2y squared minus 3y. Okay, and then let's keep going. Raised power divided by new power respect to y. So I have 2y cubed divided by 3 minus 3y squared over 2 from 0 to 6. So we have 2/3 6 cubed minus 3 6 squared over 2. Subtract. This one, if you plug it in, you see that it's gonna be 0. Okay, so let's keep going. I'm going to make this smaller. Okay. All right, so I have 6 cubed divided by 3 times 2. So first number, I get 144. I have 6 squared divided by 2 times 3. I have 54. So 144 minus 54, I get the final answer of 90. Okay. So when it says use the description, make sure you're looking at which one is a function and which one is a number. Okay. If x value is a function, then you are having a double integral over the regular y region. If y variable is a function value, then you're having a double integral over the x region. Okay, moving along to the third example. Graph the region R bounded by the graph of the indicated equation. Describe R in the set notation with double inequalities and evaluate the indicated integral. So we have a y as 1 plus 6x minus x squared, and then y all the way up to 1. And then the function is we are integrating over 15x dA. Now, let's take a look. Let's define. Let's come up with something like this here, right? Definition. So my R of x, x comma y. Now notice the y value is given. So we are integrating from these two. So this is a function value. Now I'm going to use a graphing calculator just to see what's going on. So if I put these two graphs, so let's do that. So it was, one of them was 1 plus 6x minus x squared. And then the second function was y equal 1. And let's hit graph. You see a parabola, right? You see a parabola intersecting line. Well, that's kind of obvious, right? The x squared function is a parabola, y equal 1 is a horizontal line. So there is a two intersection point right over here and then right over here. Let's find the intersection point to get the accurate answer. I'm going to screenshot this one. So to find the intersection point, you press the second key, trace, number 5, intersect. And then you trace, and then hit enter, right bound, and then enter twice. And it's gonna ask you to guess enter 3 times. Let's try one more time. Second, calc, intersect. First one here, and then second right bound here. Okay, this is acting a little bit different here, and then here. Intersection. Okay, let me see if the other calculator is a better one, because the actual and then computer calculator is a little different. So let me see if this works better. 1 plus 6x x minus x squared, and then second function is y equal 1, graph. There you go. Let me do the window. It's too big, so -10, +10, -10, +10, graph. There you go. So you see these 2 points, and I'm going to do calc. I'm not familiar with this calculator setup. There should be a second trace. Oops, okay, and then where's the trace button? You know what? All right, I'll just open up my computer. Actually, I'll use actual calculator function. Actual calculator. Okay, so this is actual physical calculator. I work better because the calculator app is set up a little bit differently, so I'll actually show it to you here. So you guys have these physical calculator as well. So first of all, let me pull out my notes and then graph those two functions again. So on y equal to, let's enter that, 1 plus 6x minus x squared. And then the second function is y equal 1. And you have this graph here, parabola intersecting a line. Now, with my calculator app, I couldn't do this one properly, so I just switched out to this physical calculator. So second calc, I couldn't find it it didn't work properly. So intersect, it's gonna ask first curve. So you kind of wanna, there's two intersection point here and here. So you want to first have a curve that is close to the first intersection point. So that point's right here, tracing kind of like moving along. That looks pretty close. So you just guess it here. And second curve, you want to get close to this first intersection point somewhere here. It's going to ask you to guess, but here you're going to just hit enter. Negative 1.45 e to the negative 15, that's a scientific notation, 10 to the negative 15. So it's like really 0. So 0, 1 is a first intersection point. So note, okay, so that we don't forget, I'm going to put it over here. The first intersection point that we have is 0.1. Okay, let's do the second one. Second trace. And then intersect number 5. And then this time you want to move along the cursor close to this point right over here, because there's two intersection point. And hit enter. And then same thing here. You want to go kind of close to this, enter it. And then the other intersection point is 6, 1. Okay. So I'm going to go back. Okay, so we tried 3 different calculators. So the actual physical calculator did work. So we found that the two intersection point, actually, this was what we had. Right? So this point right over here is y equal 1, this curve here, the black curve. Let's actually color code it. So y equal 1 is this black curve. Now the blue curve is y equal 1 plus 6x minus x squared. And then this intersection point right over here and right over here, that was 0, 1, and then 6, 1. So looks like my graph of region R, this is my region R covered by this area. So that will be the graph. So we got that. Now in terms of defining the function, so we have R, right? Now the y value is already given. So y is between 1 all the way up to, so starting with 1 all the way up to this whole entire curve, which is 1 plus 6x minus x squared. Now for x value is the number. X value, oops. Sorry, my mistake. When I wrote it on the notes, I mixed up the points. 1, 0, it was 6, 1. Right? So x value goes from 1 to 6. There you go. So that will be my R defined. Now take a look. Y function is a y value is a function. So I'm having a regular x region. Notice y is a function. X is my number. So I'm going to have my first definition right over here. So we integrate y first and then x. So that's how you know which one to integrate. So we will integrate the dy dx. So my integral will look like this. Dy dx, so x term goes outside. So one, oh, no. I did it right on the original. 0 to 1. That was the intersection point, right? Sorry for messing up. So 0 to 6, and then we integrate from 1 to 1 plus 6x minus x squared. My function is 15x dy dx. dy dx, that means x is a constant, so when you integrate, I gain a power, so I have 0 to 6. It looks like I'm going to have 15xy, right? Integrating from y equal 1, y equal 1 plus 6x minus x squared dx. Okay, let's keep going. Now evaluating from 0 to 6. 15x, y is 1 plus 6x minus x squared, minus 15 x times 1 dx. 0 to 6. Now I'm going to distribute this. So I have 15x plus 15 times 6, 90x squared minus 15x cubed minus 15, right, x dx. 0 to 6, 15 disappear. So I have 90x squared minus 15x cubed dx. Let's keep going. Let's integrate it for the second time. So my integration, now gain power divided by new power. So 90x cubed over 3 minus 15x to the 4th over 4 from 0 to 6. So 90 divided by 3, that's 30x cubed minus 15x to the 4th over 4 from 0 to 6. So let's see. 30 times 6 cubed minus 15, 6 to the 4th power divided by 4 minus, rest of them, this is a 0 minus 0. So that's pretty easy. For the first number, 6 cubed times 30, I have 6,480 minus 6 raised to the 4th power times 15 divided by 4, I get 4,860. So my final answer end up being 1620. So the area is 1620 units square. Okay. So quickly recap, I noticed the y function is y value, the variable y is a function. So I did that. I graphed it to find my x value. Where are the region that is intersected by these two curves? Where does it start? 0, 1 all the way up to 0, 6, 1. So 0 and 6 is your x value. So you see that y value is a function, x value is a number. So that is a first definition, regular x region. Y value is a function, x value is a number. So we do dy and then dx. So I set that up, evaluate it, and then end up getting 1620. 1620 is the final answer. Okay. So let's